Looks like we're still a little bit blurry on here. Still trying to remember to write big again. Before we start, are there any questions that people have about the midterm? That you have? Alright. Then let's get started. So last time we were talking about matchings in graphs and particularly matchings in bipartite graphs. And we proved Hall's matching theorem. And so today, that was like a pretty involved proof. So today I wanted to do kind of like less proof focused and more like algorithm and example driven. So the first thing that we're going to do is look at how to find maximum matchings. So just like to remind you from last time, we had maximal matchings and maximum matchings. Maximal was like you can't add another edge to get a larger matching, and maximum means that it has the maximum size among all possible matchings. So we'll look into an algorithm for how to find maximum matchings. And this is going to use the idea of M alternating paths from last time. So yeah, maybe I'll just write down what this is. So maximum matching is maximum size among all matchings. And then we also had M alternating paths. So if M is a matching, then an M alternating path is a path where every other edge is in M and every other edge is not in M. So a path with every other edge in M. And then one other idea that we're going to need for this is an M augmenting path. So this is an M alternating path whose endpoints are unsaturated. So the key example here is the path with 4 vertices and M just being this single edge in the middle. Then in this case, this is an M alternating path and the endpoints are unsaturated. And the point of this is that we can enlarge the matching by swapping out, removing this edge and instead including the 2 outer edges. So the basic idea behind looking for a maximum matching is going to be to search the graph for M augmenting paths and then just increase the size by doing that swap. So that's kind of the overall strategy. Okay, so there's a theorem to this effect that I'll just state and not prove. So the theorem says that a matching I don't call it M in a graph is maximum if and only if there's no M augmenting path. Does this make sense just on an intuitive level why this would be true? Yeah,
What about the backwards direction for this one? He like sketched that pretty cool.
so if there's no M augmenting path, then why is it maximum? I did not prepare a proof, but we could look at it. So we'll pull open the. Just trying to find the. Actually can't even find where this is stated right now. But I know that it is in the book somewhere. Yeah, I think have a look, and if you have questions about it, then we can discuss. Where can I find this? Okay, so how are we going to go about finding maximum matchings? We're gonna present first an algorithm for finding M augmenting paths, and then that algorithm will get successively applied to a specific matching in order to slowly increase its size until there is no M augmenting path left. Okay, so let's see the algorithm for finding an M augmenting path. Okay, so, and this is just going to be in a bipartite graph. So the input is going to be an XY bigraph G, a matching M in G. And we're also going to let U be the set of M unsaturated vertices in X. Okay, so let me just draw a picture quickly. So let's see, these are our vertices X. And this is Y. And then maybe here's how our matching looks. Then these vertices are U. And maybe I should draw some other edges as well. Oops. Okay, so the idea is that we're going to start in U and explore M alternating paths coming out of here. And then we'll let S be the set of vertices reached. So this is kind of like the proof from last time. So any vertex, and I didn't make this connected. Here we go. So if we reach a vertex via an M alternating path, then S is going to be that set of vertices in X, and T is going to be that set of vertices in Y. So for example, this vertex. And then we're going to mark off the vertices that have been explored for path extensions. So say like we want to check paths coming out of this vertex, then we know that we can reach this one, and so eventually we'll want to explore all of the possible paths coming out of this vertex as well. I think I still need to make this maybe a little bit more interesting. Okay, so that's so yeah, let me write down the idea. So the idea, we'll explore M alternating paths from U, and we'll let S, which is a subset of X, be the vertices, and we'll also let T subset Y be the vertices reached by M alternating paths. And then we're also going to check vertices of S for path extensions. Okay, so to start with, so for our initialization, I'm going to start with S equal to U and T being the empty set. And then for our iteration, so I'm going to mark off the vertices. At each step, I'm going to mark off the vertices in S that have been checked. So to start with, I'm going to select an unmarked vertex in S to work with. So if S has no unmarked vertex, then we'll stop and return M as a maximum matching. So that would mean that it has no augmenting paths. Right now we're looking for an augmenting path. And then otherwise, I'm going to select an unmarked X from S. And then I'm going to explore that vertex. So to explore X, I'm going to consider every Y in its neighborhood such that X, Y is not in the matching. Right, because like, what are we looking for? We're looking for an M augmenting path. So I want to find a path that starts with a blue edge, right? So if I go back to my picture, maybe this is X, and then, or so let's say this is X. So then my possible Ys would be this vertex and this vertex, but not this one, because we want a path that starts with a blue edge. If Y is unsaturated, because I also want to be able to exit via a red edge, then I'm gonna terminate and report. Oh no, sorry, I have this backwards. So, oh wait, let me just finish the sentence, then I'll explain what's going on. So I'm going to terminate and report an M augmenting path from U to Y. Sorry, little y. Okay, so let me go back and explain. So like, let's say this is my vertex X. So we know already that in previous steps of the algorithm, perhaps we've reached X via a path that started with a blue edge and then entered X via a red edge. So if I find a blue edge coming out of X that goes to an unsaturated vertex, then I have found an M augmenting path that's as long as possible, right? So that's like what this case is applying to. Okay, so if Y is unsaturated, then we terminate and report that M augmenting path. Otherwise, otherwise Y is saturated, so it's matched to some W in X. By M. So in that case, I'm going to add Y to T and W to S. And then after exploring all edges incident to X, then I will mark X off. So after exploring all edges from X, then I will mark X and iterate. Okay, so that's the algorithm. Are there questions before we jump into an example? Yeah.
Why do we, oh, never mind.
Okay. Answered your own question. Yeah. Other questions? Okay, so I'm gonna draw an example graph and then have you run through the algorithm to find an M augmenting path. Okay, so that's the graph. So go ahead and find an M augmenting path using the algorithm. Okay, do you need more time or did you come up with more time? Okay. So I think to some extent, this just depends on what order you decide to check the explore vertices in. Um, so for example, like one thing that you could do is start with this vertex. So then we would go along blue edges to Y. So let me actually label these X and Y. So we'll travel along a blue edge to Y. And then if this vertex is unsaturated, then I would stop, but otherwise then I include the vertex that's on the other side now also in my set S. So I'll do that. And I'll mark that I already checked this vertex. And then from this vertex, I could explore this edge and find that this vertex is unsaturated. And so then I would return this as my M alternating path. Another option, I could have explored this edge and discovered this M alternating path. So I think there's like, it kind of depends on the order that you go in. You'll find different things. After having done an example, were there questions that anyone had? So by the way, going back to this theorem, this is theorem 3.1.10 in the book. And the proof for the reverse direction is a little bit involved. So yeah, you can have a look at that. It's not like long, but it does like rely on a lemma and a construction and stuff like that. Yeah.
So this is just any M augmented path of the maximum path.
Yeah, so this would just find you one M augmenting path. So then so yeah, next step to find a maximum matching, we need to repeatedly apply this algorithm to find a maximum matching. So yeah, so that's gonna be the next like theorem, I guess. So repeatedly applying the augmenting path algorithm to a bipartite graph produces a maximal matching.
Maximum, right?
Or yeah, maximum. Yeah, thank you. Okay, so go ahead and try that for this example. So just repeatedly apply the augmenting path algorithm, and we may come up with different matchings, but in the end, the size should be the same, and that should be maximum. So I'm also just gonna do this while you all work on it. Did you all finish or do you want more time? Did anyone find a different matching than this one? A different maximum matching? I think it's like, so one thing is it's pretty easy to check that this is a maximum matching because it saturates X, so it's not possible for us to include any more edges. Are there questions about any of this stuff? Okay, so now we're gonna kind of generalize this idea of matchings in bipartite graphs to in like two ways. So one is looking at more general graphs, and then the other one is going to be looking at different types of spanning subgraphs. Right, so a matching is like a spanning subgraph where your graph is just a disjoint collection of edges. So we'll look at different types of spanning subgraphs as well as just different like graphs. Yeah.
Could you highlight,
Oh, the edges that I
can't see the colors.
tossed.
Yeah,
Oh, yeah.
the maximum.
Yeah. Wait, is blue and red bad?
For some reason, I don't see. I didn't see when you did it the first time, version. Is it just the? Would be,
Okay, so the ones that I got rid of were this and this.
you got rid of those?
Yeah, I think those used to be in the matching and then I took them out.
Oh, okay. I
Yeah.
probably didn't look up when they were there. Okay.
Oh, okay, yeah, I should have just like duplicated the original graph before I started changing things. So yeah, so okay, actually I think I can just undo. Okay, so that's what it looked like to start with. And then so I found the first path and took out that, and then the second one. I took out that. Yeah. Yeah, are all of the colors that I use like legible for everybody? Okay, yeah, you can let me know if that's ever an issue. Okay, so let's start with a definition. So a factor of a graph G is just a spanning subgraph of G. And then a K factor is a K regular spanning subgraph. So matchings are one factors. For example, can anyone think of another example of like where we've already seen this idea in some form in this course? I guess we've talked about spanning trees, but that's not the same exact thing because the trees don't have, they're not K regular for any K. We kind of touched on this when, like, way back when we were talking about Eulerian circuits, except that those were allowed to pass through the same vertex more than once. So I guess if your Eulerian circuit is a cycle, then that would be like a 2 factor. Okay, so just to work through an example. Let's look at this graph. See how many vertices. And find an example of a K factor for K from 0 to 4. If it's a spanning cycle, yeah. Okay, let's go through the examples. So for k equals 0, what is a 0 factor? Yeah, so okay, so it has to be, so it's a subgraph and it has to be spanning, and every vertex has to have degree 0. So it's just gonna be all of the vertices individually with no edges. Does that make sense? Okay, and then what about for a 1 factor? Yeah. Yeah, so this, I feel like this graph, it's in this one, it's not too hard to do because there's not that much going on. So maybe just take something like that. Okay, so I think that does it. And then, okay, let's skip ahead to 3. How can I find from this? How could I find a 3 factor? Yeah, because in this graph, so this one's special because it's 4 regular, right? So I can take the complement and get a 3 factor. So just highlight that here. Oh yeah, and of course I need to include the vertices here too. Okay, so that's our 3 factor. And then what about for a 2 factor? Yeah. Yeah, so we could take like this, the outer 4 cycle, and then the inner like 6 cycle. Okay, and then what about for 4 factor? Yeah, it's just like this whole. Make the whole thing red. Okay. Okay, are there questions? Yeah.
Did it regraph? Can you repeat why it's the complement?
Yeah, so in this case, because this graph is 4 regular. So if I have already found a 1 regular subgraph, then the complement will be 3 regular. Yeah. Does that make sense? Okay, so kind of as we've observed, the the edges of a 1 factor give you a perfect matching. And so kind of the question that we've been looking at is for bipartite graphs. When do we have a 1 factor? And there's a generalization of this given by Tutt. So Tutt gives a necessary and sufficient condition for as a 1 factor. Okay, so for this, I just need to, I think there's just one definition. So an odd component of a graph is a component with an odd number of vertices. And I'm gonna let O of G, little o of G, denote the number of odd components. Okay, so let's consider, so we're gonna like do some reasoning to find a sufficient condition, and this will end up being called Tutt's condition that is also turns out to be sufficient. So, okay, so let's say we have a graph G. So if G has a one factor, and we consider a set S of the vertices, then let's think about what G minus S looks like. So, so we'll draw a picture. So let's say this is our set of vertices S. Okay, then let's look at like what can G minus S or like let's think about what could be going on in G outside of S. So if you have a component that's separate from this, these would have to be even because we have one factors. So if these don't have any edges going to S, then every edge of the one factor has to be contained inside of here. So these would have to be even, but we might have some odd components sitting like this that do share an edge to S. So these would be odd. So let me write down a sentence. So if we consider a set S of the vertices, then every odd component of G minus S has a vertex matched to something outside of it. And this, you know, where could it be matched to? This has to be something in S. So which? So we're assuming that we have a one factor. So I'm kind of conflating the one factor and matching. So like, okay, maybe I should, I'm gonna replace this with a specific example. So, or like, let's actually just go back to this graph. Okay, so let's have a look at this one. So here we have a one factor. So let's pick a set of I don't know if I'm gonna be able to pick a set S that like really disconnects this. Let me make a different example. Okay, so here is a graph and it has a one factor. If this is my set S, then G minus S has like these three components. Right? And all this is saying is the odd components have to have an edge going back into S because this vertex has to get matched to something via an edge that got deleted. Yeah. Does that make sense? So furthermore, the vertices of S that, and you know what, actually, I'm gonna make us have multiple odd components just to illustrate the next point. So I'm gonna change my S. I'm gonna make S this. Okay, and then I have this is another odd component. Okay, so every odd component is matched to something in S. And furthermore, those have to be distinct vertices of S because every vertex is only contained in one edge in the one factor, right? So this is one of my edges going from an odd component to S. Here's another such edge, and their endpoints in S have to be distinct. So since these vertices of S must be distinct, we have an inequality. So the number of odd components of G minus S has to be less than or equal to the size of S. Does that make sense? So this gives us Tut's condition. Yeah, it doesn't guarantee it. Yeah. Yeah, because you can imagine like yeah, like let's say this just doesn't exist or something. There's still vertices of S that are like left out from the, yeah. Other questions? So I'll write down Tut's condition. So it says for all subsets S of the vertices, we have to satisfy OG minus S is less than or equal to the size of S. Okay, so here's what the theorem says. And this is called, I think, Tutt's one-factor theorem. And it says that a graph G has a one factor if and only if Tutt's condition is satisfied. So O of G minus S is less than or equal to the size of S for every S subset V of G. Is that the wind? That's wow.
I think it's that Windows open.
Oh, I'll close them. I mean, I know it was supposed to be like really windy today. There was like some kind of like warning. Okay, are there questions about the theorem? So, the proof of this is like super long. I think it's like 2 full pages in the textbook, where usually the proofs that we go over are like a paragraph or something. So instead of going over it, I'm going to focus on kind of like corollaries and consequences. So let's take a look at a corollary. So this is every 3 regular graph with no cut edge has a one factor. So I'm gonna give you maybe like 5 minutes to think about how to prove this from Tutt's theorem. So the hint is there's a corollary of Tutt's one factor theorem. So you should try and verify that this condition holds for any set S. Okay, should we talk about the proof? So this like kind of relies on counting, which I feel like is a theme among any statement that talks about like a regular, like k-regular graphs, you end up like counting things. So let's prove this. So let's let G be a 3 regular graph with no cut edge. And then we're just going to show that G has to satisfy Tut's condition, which will then imply that it has a 1 factor. So let's let S be a subset of the vertices of G. Then let's count the edges between S and odd components of G minus S. Let's count edges between S and odd components of G minus S. Okay, so on the one hand, like what is the maximum number of edges that could just be coming out of S? Yeah. So yeah, since G is 3 regular, every vertex of S is incident to at most 3 edges. So the number of edges leaving S is at most 3 times the size of S. Okay, on the other hand, so I'm gonna make an observation and then we will prove that, or sorry, I'm gonna, okay, I'll just write down the statement, but then we need to show that this is like actually the situation we're in. So if it happens that each odd component H of G minus S is incident to at least 3 edges, three of these edges coming out of S, so I'll just say at least 3 of these edges. So if this were the case, then we would have the following. So 3 times the number of odd components of G minus S, that has to be less than or equal to 3S. Right, because we already put an upper bound on the number of edges going between S and odd components. And so if each odd component has at least 3 of these edges, then we have this inequality. And so then we would be done. So because this implies a Tut's condition. So we're done. Okay, so now what we need to prove is that this is actually what's going on. Does it make sense so far? So if this is the case, we're done. So let's prove that this is what the situation is. So let's let M be the number of edges from H to S. Okay, then the sum of the vertex degrees in H has to be, so the whole graph is 3 regular. So the number of edges, incident to vertices in H would be 3 times the number of vertices in H, but then we have some of the edges are going to S. So, the sum of vertex degrees in H is going to be 3 times the number of vertices in H minus this number M. Does that make sense? Maybe it would help to draw a picture. So, I have to make a 3 regular graph. I'm failing spectacularly at making this 3 regular. Oh no. Okay. I think we've done it. So, okay, so let's say this is S and this is H. And then this number of edges is M. Okay, so if I want to add up all of the vertex degrees in the subgraph H, it's going to be 3 times each vertex because the original graph is 3 regular, but then we subtract off any edges that are headed towards S, which is M many edges. Does this make sense? Nobody's asking a question. I can't tell if that's because you're confused or it's good. Good.
Wait, sorry, but how, yeah, I guess I am confused, like, 'cause I'm just like looking and like counts, it's 9,
So this is like thinking of H as a subgraph, which is like G minus, so what is H? Yeah. So H is G minus S. So we would just have like this portion of the graph. Yeah. Okay, does that clear it up? Okay, so okay, so then since H is a graph, the sum of its vertex degrees has to be even. This goes back to like the handshake lemma. So the sum of the vertex degrees in H has to be even. So let's just recall the handshake lemma. What did we do when we summed up the vertex degrees? We counted every edge twice, right? Because we counted it once coming from the left vertex and once coming from the right vertex. So, so this number has to be even. So, and we know that H was supposed to be an odd component. So, okay, so 3NH minus M is even. We know that NH is odd because H was an odd component. So then what does that tell us about M? Yeah. So then M is also odd. Okay, we're very close. So we want to conclude that M is at least 3. So the only case we have to rule out now is M equals 1. So why can't M be 1? Yeah, so since there are no cut edges, M is not equal to 1. And therefore M is at least 3. And so we're done. Because going back to this, this kind of dealt with the case, if M is at least 3, then we proved that we're all set. Let me zoom out so you can see everything. It's so blurry. Okay, so that finishes the proof. Are there questions? Okay, so let's stop there for today. There are office hours today in case anyone has midterm questions. But otherwise the midterm is due Monday and I'll see you on Tuesday.